Good morning, everyone. How are we all today? Looking forward to an awesome conference? Really? Come on. It's first thing in the morning. Ah, dear. Tough crowd, eh? No, it's all right. You folks are fine. Don't worry. All right. My name is James Titcumb. I've been doing PHP since like 2002, programming since before that, like I was a kid and doing stuff on Amigas. I'm a Zen certified engineer. I help run the PHP Hampshire user group, which I founded, but I'm kind of stepping down a bit from that. And I also run the PHP South Coast conference, and it's the last year this year. So if you are around in the UK, down on the South Coast, funnily enough, then do come along. I am a consultant engineer at Rove, and we have this single Rove branded elephant at the moment. We are getting more done, but they are going to be in production at the moment, so I haven't got any more, unfortunately, before anyone asks me. All right, anyway, on to the topic of the talk. I'm going to talk to you today about climbing the abstract syntax tree, and describing what this is, what it means, and how you can understand it, right? But first of all, let's just recap or introduce you, if you don't know already, how PHP works. PHP code is fed into something called a lexer, which is basically breaks down your PHP code into these things called tokens. Each token is like, a semicolon or a string or whatever. These tokens are then taken and sent to something called a parser. The parser takes these tokens and tries to make sense of them, and it results in something called an abstract syntax tree, which is, funnily enough, the point of the talk. I'll go into a bit more about what that is exactly, but then we take this abstract syntax tree, which at the moment is perhaps an abstract concept for some of you, and is compiled by the compiler. And that generates opcodes, which you may or may not have heard of before. These opcodes are stored in the thing called an op cache, and that makes things run faster because we don't have to keep recompiling every time. And then these opcodes are executed in something called a virtual machine. This is not like Vagrant or something like that. It's a term used to describe a virtual CPU that executes these opcodes in turn, basically. So it's kind of an abstract concept. We don't have to worry about that for now. But the AST step here is actually new in PHP 7. We never had this before. It went straight from lexer to parser to compiler and store those opcodes, which is a little bit inefficient, actually. So let's have a look at the various parts of this, right? The PHP lexer is a generated program. It's a C file, right? We have this this syntax definition in Zen language scanner .l. And this is, as I said, it's a definition, and it's fed into a program called re2c, or re2c. I don't know how you say it out loud, because we never say these things out loud unless we're at a conference. But yes, so we have this definition goes into here, and this actually describes how the tokens are split out. This is an example of a few parts of that file. The format, if you've ever used something called fast lexical analyzer, or flex, which is used by HHVM as well, the format's going to be pretty similar. So in these angle brackets, we've got st in scripting. This is a state, right? And that's the required state that the lexer needs to be in to match this particular token. There's other ones like st double quotes, st here doc, st now doc, and so on. And that describes basically what kind of position you are in. Followed by the token itself. These are pretty straightforward. They're just strings, okay? I think we can understand those. And they match exactly those strings in the stream of bytes that come in. Inside the curly brace is basically what happens when these tokens are encountered. So In all these cases, it's quite straightforward. We just return the token directly, and that builds up to form the token stream. This is a slightly more complex example, but it kind of allows us to understand what the states are and what they mean. And the states allow the same tokens to be used in different ways depending on the context of where you are in the file. Let's look through bit by bit. This is the state that we need to be in. So in this case, st double quotes back quote backticks basically, or here doc. If we match this token dollar curly brace, then we do this. And we're doing this, we're calling this function called YYPushState, which is where we're basically changing the state that we're in now. So it's a state machine, basically. And then we're returning a token. And this is the second one. So this is the closing one. So if you hadn't guessed, we're in a string, basically. We're looking for a variable name at the moment. So label is basically looking for a label. That's another definition elsewhere, which we're going to go into. And then we copy the value that we match, so that label, the variable name, into a lower value. And then we change the state again back into scripting state because we've closed that string. And of course we return the token, so we add another token onto that stream. So, given that syntax definition, we've passed that into re2c, and that actually generates a C file which can be compiled independently. Won't do very much by itself, it's not all that useful. But yeah, you can run that independently and see what it does and what it generates. The C file is massive and makes no sense. So the parser. The parser actually works in quite a similar way. We have this file zendlanguageparser.y, and this contains the parser definition, and it looks something like this. It gets a little bit more complicated, but real programming languages are quite complicated. And the way PHP has grown sort of organically meant stuff has kind of just got botched in and added and so on over time. But we're trying to understand the main parts of what's going on here. These are the labels of the definitions of stuff that can happen. We have two here, if statement and if statement without else. I've not added the definition for an expression, which you'll see in or EXPR or statement, because they're quite big. And I've only got this much slide to work with, and if I put it all in there, you won't see anything. But the way this kind of works is it's kind of recursion, right? So we try and match something, and then if we find something that matches, then something else might match. So we have to look up the definition for that and match that and so on. But yes, an if statement, basically, it matches to say if we find an if statement without an else on its own, we can basically ignore this, but it's to do with precedence operators. This says it's left associative, if that means anything to anyone. It's not too important for this. Or we match an if statement without else, followed by a statement. But to find out what an if statement without else actually means, we have to look at that definition. So what I mean, you recurse down through it and figure out what this actually means and provide some meaning to it. So if you find the if token followed by a literal surround of parentheses with an expression in, followed by a statement, then we match. Great. Yes, and if we find an if statement without else, followed by else if, followed by an expression surrounded by parentheses, you can see they're written in literals, followed by another statement, and then that also matches. Let's try and kind of visualize this with some code, because that seems a bit confusing perhaps. So first of all, this block here matches an if statement without else. I think that should actually be down to the next parentheses. I've done the slide wrong, apologies. Oh no, I haven't. So the outer one also matches an if statement without else. So we've got a nested matching here. And then the outer one matches an if statement, because it's got an if statement without else, and then the word else, and then a statement in it. Does that make sense? I got some nods, cool, good. This stuff here is is what to do when we match this this grammar. Now, there's something important here. This is taken from PHP 7.0.10, but here we can see we're calling these AST functions: Zend AST list add, Zend AST create list, and so on. And this is what forms the abstract syntax tree. If we have a look at PHP 5.6, this does a Zend do if cond function call. Great naming, right? But it calls this block of code, and if we look through and try and sort of understand what's going on here, we're actually creating an opcode here directly. So we're creating an opcode and passing that on down the chain. So there's this new thing, this abstract syntax tree. So going back to the first diagram, the result of the parser in PHP 7 is the AST, right? That's fed into the compiler, which translates into the opcodes, and then the opcodes are then executed. Let's try and simplify this a bit. Have I lost some of you already? A few nods, okay. All right. What is it? All right, I've mentioned it a lot now. But what is an abstract syntax tree? It's a data structure that describes your code. It's a representation of some code. It uses a non-PHP data structure, obviously. It can be modified, not in userland at the moment. Well, maybe. We'll see. And that modifies the behavior of the code, of course. It contains metadata as well. Like, for example, what line, what column, what file, and so on. And an AST can be unparsed. Unparsed is basically regenerating or printing out the code that we understood from the abstract syntax tree. The layout may change because we don't have all of the information about how we're structuring everything. Does the audio sound weird? Can we sort that out? I don't know how to do that. So. Anyway, so we got some PHP code. We know what this does, hopefully. And this is an AST representation of it. It's not the AST representation because there isn't a single representation of it. Okay, I think it's gone down a bit, that's better. So yeah, it's represented as a tree, funnily enough, because that's in the name abstract syntax tree. We've got an echo statement, and the sub-value there is a string with the value hello world. And that's all we need to represent that piece of code. Louder, sorry? Yeah, I know. They're looking very lost and confused in there. I don't know. Okay, I'll try and go on. No, we'll pause a moment. Sorry about this, folks. As a game, if you can hear me, can you maybe guess what the AST for this might look like? Feel free to shout out. Yeah. They can't hear me on the camera anyway, so. Say again. Okay. All right. Any other guesses? Yeah? That sounds like something we'll see. I'm not going to move the slides on yet, because just for the video. But hopefully we get the sound sorted soon. This is exciting. Technical issues. Love it. Room full of technical people.
1, 2, 1, 2. Try with this one.
Okay. All right. Shall I take this one?
No, because you need it for the camera.
Okay. Okay.
Okay, can you hear me now? Yeah, lots of nods. Okay. All right. So, yes, if you didn't hear the chap at the front, basically we've got the same thing, but instead we've got a concatenation operator now that we've added. It seems like a fairly trivial change, but suddenly our AST actually gets a lot bigger. So we start with an echo statement at the top, just like before, because we're doing an echo. We have a concatenation node now in the tree, and we've got a left and a right value. That's because a concatenation is called a binary operator. It's got two operators to it, the left and the right. It doesn't actually matter in the case of concatenation, perhaps, or addition, and things like that, because it doesn't matter which way around those operators go, they're always going to result in the same thing. It does matter here, because otherwise, if you do this in the wrong order, you're going to get world hello space, which is not what we want, right? So let's do some maths, or math if you're American. We're going to assign some variables. A is 5, B is 3, and we're going to echo A plus brackets B times 2. And it looks a bit like this. It's gotten even bigger, right? This is fairly simple PHP code, but we've got quite a big statement going on here. So we've got an assign statement. The variable name is A, integer value 5, and so on. And then we've got our add operation. We've got a left operator, which is variable A. And then on the right-hand side, we've got our multiply operation, which also has a left and a right. The left is variable B, and the right is just a constant integer of value 2. All right, so why is the AST better? It's actually allows us to be faster. The tree structure is nice, and it's quicker to traverse than just getting this whole stream of opcodes and so on. It's also a nice logical representation. You can kind of look at these graphs, and with a bit of reading through it, you can understand what's going on, and it gives you that nice organized structure. And obviously that's good for computers as well. And the nice thing is you can do optimization, so you can optimize out inefficiency. And you can reduce constant nodes. So if you've got a statement, not that you would, but if you've got $A equals 1 plus 1, you know, we could take that AST and say, well, those are constant values. They're always going to add up to 2. So we can just replace that add node with the value 2. I don't think PHP does things like that too much yet, but there is lots of scope for doing things like that. So it's a tree, right? We can structure it like this. This is the same piece of code, but I've done it in a nice graph. And when we show it as a tree, we can do something kind of interesting. We can follow a line around the graph, around the outside of the graph, and touch each node as we go around. And something interesting happens. This is something called a pre-order traversal. It's also called Polish notation. If you write down each node as you traverse through it, it produces this kind of output. The important thing is the operation or statement is prefixed, right? It comes before. And the arguments for that operation are afterwards. And it's kind of interesting because it allows us to see the order of precedence very easily. When writing programming languages, like PHP or whatever, the order of precedence is very important. Take, for example, 1 plus 2 times 3. Depending on which operator, plus or multiply, is more important in the order of precedence, those two sums will produce different outputs. So we need to define this order of precedence. I mean, obviously in normal mathematics, multiply has higher precedence, so the correct answer is 7. But maybe you want a really weird programming language that disobeys the rules of mathematics, and it might produce 9. But the point is you've defined that. So when we write this out in this Polish notation, it will look something like this. Plus 1 times 2, 3. What? That's completely wrong. But it is logical and it works. That's how these things work, right? We have the operator, which is plus. The first operator is plus. We have a left operand, which is 1. And then we have a right operand, which is another sum. So we examine this again. We've got our operator on the left, multiply. We've got a left operand of 2 and a right operand of 3. All right? Now, if we evaluate these from the innermost part outwards, obviously 2 times 3 is 6, plus 1, we get 7. All right? And we can see that because we've defined that order of precedence. Now, there's also something called a reverse Polish notation, where the same thing would be written 1, 2, 3 times plus. What are you going on about, James? All right, but we can use these in a certain way. We can build a stack out of these, all right? A stack. If you don't know what a stack is, it's just let's think of it as an array, okay? Pushing and popping things into that's right, into the array and off of the array. So if we look at the first value is 1, we put that into the stack. The next value is 2, we put that into the stack. And the next value is 3, and we put that into the stack. And we're stepping through character by character, or item by item. The next one is multiply. Now multiply is an operator, so we need to operate. And we take two operands off of the stack, 2 and 3. And we put the result back onto the stack.
So now we've got 1 followed by 6 in the stack. The next is also an operator. We know it takes 2 operands, so we take the 1 and the 6 off the stack and put the result back on the stack. And that's the end result. Hopefully at the end you have only one thing in the stack, otherwise maybe something's broken. We didn't do something properly. But okay, let's write a compiler in 3 easy steps. Because we're armed with some pretty dangerous knowledge, but let's kind of put it into context. Don't use in production. All right. You can actually follow along in GitHub if you have a laptop. I can't see any laptops out, but you can do. There's this repository on my GitHub, basic-maths-compiler, and you can follow along if you like and see the full code. All open source, so feel free to tell me how terrible it is, because it is pretty terrible, right? But I'm trying to demonstrate concepts here, not write an amazing compiler and things like that. All right. First up, we need to define our language. So we're going to just say, well, we want some basic sums, okay? We're going to only use positive integers as inputs. Anything else is invalid. We're going to allow white space, but it's ignored. We're going to have the 4 operators, add, subtract, multiply, divide. And we're only going to support 1 line of input. And there is going to be also no way to override the order of precedence. So whatever is defined in the engine, that's what goes. You might see these tokens. So we defined our tokens. So we're going to start off by writing a lexer. A lexer can be written as just a load of regular expressions. I've written them out individually here. So we've got add, subtract, multiply, divide, integer. We'd only take positive integers, so we don't need to account for a negative sign. And white space. Now, I know Nikita Popov in the back there has found a way to sort of meld those into one big regex for example's sake, but I'm not going to go into that because regex blows my mind. I just want to also point out that all of these anchor to the start of the string. They've got the little circumflex character, and that means we make sure that we're only matching the next character, not somewhere else further down in the string, because that might produce some undesirable results. So, basically what we're going to do is we're going to step through the string bit by bit, analyze from whatever offset we're at, so we start at 0, obviously, and every time we match one of those regular expressions. We move the offset on by the length of what's technically known as a lexeme, or the token that got matched. And this is the matching method, okay? This is pretty straightforward stuff. We're going to loop through each of the patterns that we've defined, so that's where that inefficiency I mentioned about crunching those up into one regex can disappear, but yes, it's inefficient. And if one matches, then we create a token object, return it with the value that we've matched, and so on. The lexeme. Alright, so we've got a load of tokens now. Let's move on to parsing them. So, as I mentioned, we need to define
Our order of precedence. We're going to say that multiply has the highest precedence and subtract has the lowest. So they're actually
in reverse order. The higher the number, the more important the operator. So, we're going to loop over the tokens here. So basically, until we run out of tokens, we're going to loop over them. We've got two stacks. We've got a token stack and an operator stack. So as we step through all of these tokens, if we find an operator, we're going to do something special. So I've cut that bit of code out and I put it here because it's quite large. There's a lot going on here. Basically, each operator token is pushed onto the operator stack. However, on each iteration, then we loop through the operator stack and find out if we've got any that are of higher precedence than the one we're on. If we do, we're going to pop it from the operator stack and push it onto the output stack. Okay? And then at the end of this loop, we pop off any operators and put them onto the output stack. So basically, we've taken these tokens and we've just put them in an order. Let's look at this in a slightly different way. This is some visualization, maybe it'll help you understand what's going on here. So we take the first is a value, so we put that into the output stack. The next token is the add operator. There's nothing already higher operator precedence in the stack, so we just add it straight in there. The next is a value, we put that onto the output stack. The next is an operator, and because it's of higher precedence, that's okay. We can add it straight on there. We don't need to pop anything off yet. And finally, we add the last value onto the output stack. And then at the end, you remember, we pop off all of the operators and put them onto the output stack. That look familiar? So we have this stack of tokens in now reverse Polish notation order. We can use a very simple stack compiler pattern to do that. That's to deal with this after this. We can just progress through the stack one by one. IP stands for instruction pointer, and it defines where we are in the stack.
And for each of those, the values, the integers that we do, we can create an AST node. So this is a integer value node. It's just a class. There's nothing too special going on here. And we put the lexeme into it, but we cast it to an integer because it's an integer, right? If it's an operator, we need to actually perform some kind of an operation here. We need to create the specific kind of AST node. In this case, I've left it dynamic. We've figured out the node type. All the source code on GitHub has all this, so all the important, the actual execution of it is all there. And we end up with something looking like this. Great. So we've got an add node with an integer value 1. We're multiplying it, and we've got two operands. They're the left and the right operand, as we expect. Good. All right. Now we have this AST. We need to execute it. So this is our main compile node function. Funnily enough, it takes a node as the parameter, and we check the type of it. If it's a binary operator, call another function, which we'll have a look at in a moment. If it's a scalar, we can just return the value. We don't have any other nodes in our AST, so that's all there is to it. And if it is a binary operator, first of all, we don't know what the left and the right are. So we actually need to compile those nodes. So that's a stepping down the tree and figuring out what everything is. And it recurses down through this tree. So if it is another sum or operator with operands, then that's going to get processed by the compile node function. If it's just a scalar value, then we just return the value directly. So once we have the compiled left and right nodes, we can find out what kind of node we are and perform the right kind of operation. Add, subtract, multiply, or divide. It's fairly straightforward. And we just perform that on the operands that we're given. So what does that mean for me, right? On the surface, this doesn't seem very relevant to your day-to-day work. But it does affect you because it allows you to have faster and more efficient code. We can offload those optimizations that we've spent so many hours, maybe days, arguing about. Oh, should you use a double quoted string or a single quoted string? Oh, I don't know, which is faster. You don't have to worry about stuff like that because that's handled by the engine. And there are some really brilliant minds who write that stuff, so we don't have to worry about it, and we can just write some sloppy PHP code, and we're fine. Maybe not a great attitude to have. But yeah, the AST is one of the reasons that PHP 7 and above is faster. And there's lots more scope, as I kind of touched on earlier, to optimize that even further. And knowing how the engine works is kind of useful, because now, hopefully, you can see, oh yes, this is how it all goes together. Interestingly enough, the AST isn't specific to PHP. It's not a PHP concept. It's just a general programming language concept. And hopefully you can actually see how other languages work, because they all pretty much do the same sort of thing. The same kind of lexing and parsing and so on. Most of them, maybe not all of them. So one last thing. AST and userland. By userland, if you don't know the term, it means just in plain PHP stuff, right? This is what we normally write. We don't normally write C code or write compilers in PHP. There is at least one person in this room that has written a compiler in PHP, probably. Anyway, why? Well, you can get huge insights into your code. You can see what's going on. You can examine the structure of your code and do magic things. So first up, there's an extension for PHP 7 and upwards that allows you to access this AST in PHP of a PHP file, because normally you can't access all this information. So this extension, written by Nikita Popov, exposes the AST to userland so that you can see what's going on. The downside is it requires an extension to install, so maybe not use it in production. Depends on what you're trying to do. But an example usage of this is we have some PHP code. I've just written in a string. You can do it how you want, pass in a file or whatever. We've got this AST dump function, which we're dumping the value of AST passcode. AST dump is just a kind of a useful method that makes the display of the AST nicer because it's huge, it's massive, right? The more code we have, exponentially bigger this AST gets. But the parse code is the function that does all the work. It takes that code that you've given it, it runs it through the lexer, the parser, and we get the AST back out, basically. It's all represented as objects, so you can go ahead and sort of traverse through those however you might see fit. There's also another one, I think it's kind of mostly unmaintained, but it's kind of an interesting one. ASTKit is another extension. It's written by Sarah Goldman. And this one actually allows modification of the AST. And then you can execute that modified code. In essence, what that gives you is something called monkey patching. It's kind of cool. there's a downside to it. Of course, it's an extension. And Sarah's probably said it's probably deprecated. I wouldn't bother using it for anything serious. But it was a fun little experiment, and you can go ahead and modify things. So, say, for example, we have this if true, this is a triumph, else the cake is a lie. This example is just taken from the README. I didn't write this. We parse that, and then we can actually graft a false, and basically graft is replacing that true node with a false value. And then we can execute it, and we get a different result the second time. That's kind of fun. All right, let's go into userland now, because that's what we're supposed to be talking about, right? PhpParser is a library, again, written by Nikita Popov. It's more or less the same as the AST extension, the PHP AST extension, but it's written in PHP. So it's a PHP parser written in PHP. Yes. The upsides to this is it's not an extension. It's very easy to use, and you install it with Composer the usual way. The downside is it's much, 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 much slower, because it's doing all this lexing and parsing in userland. I've only briefly looked into how it works, but it does work in a very similar concept. It's got the definitions of the lexing and parsing and so on embedded in it, and I believe it uses the re2c as well, perhaps. But this is how you use it, and it's kind of very similar to the way we'd use the extension, PHP AST extension. We create the parser factory, which will create the parser itself. We can give it a string of code, and it will return the abstract syntax tree. So we can pass in a file and see what it's got in it. And we can print that out, and we can see loads of output, depending on how big it is, of course. And there's one more library. This is kind of a shameless self-plug. But it's a library called Better Reflection. It's written by me and Marco Pivetta. And in short, it's the reflection API mirrored completely in PHP. But instead of using reflection, it actually uses the AST. It's pretty flexible, pretty powerful, and interestingly, it allows monkey patching. So the workflow of this is we have this thing called a reflector. We have a source locator, PhpParser is used by this, that parses the code into AST, because there's no point in rewriting the same thing that already exists, right? And Nikita's generously put that code in so that everyone can use it. And then we return the reflection itself. And we've tried to keep the API as similar as possible to the reflection that you may be used to. It's quite similar, but not exactly the same. It would look something like this: reflection class, create from name. And this uses a load of defaults, which we'll have a look at in just a sec. It uses this under the hood component called a class reflector. So we can see here we build a default reflector, sorry if you didn't hear that, and it called reflect on that and pass the class name in. This is what the default reflector looks like. We've got we've wrapped it in an aggregate, which basically means we can chain multiple source locators together. Don't worry about if you don't know what a source locator is. We'll have a look at that in a moment. We parse in a PHP internal source eval code for people who do evil evaling. And then an autoload source locator, which is kind of fun. But yeah, we give it a class structure, something like this, and we come out with an AST that looks something like this. The source locators are kind of interesting. The autoload source locator works in quite a fun way, because we actually hijack PHP files stream. So when you require a file, like Composer does usually to include some code, we hijack that process and we look for the file name that you're trying to load, and then we return that out, and then we can actually load that ourselves, pass that into PhpParser and get the AST from it without ever having to actually load that class into PHP memory. That allows us quite a fun little thing to do, where we can change the structure of that AST and then execute it. So then we have monkey patched code in userland. As I said, it's not particularly fast, but the master branch of Better Reflection can do that, and it's kind of fun. And you register an autoloader so that when you do actually use the class, it hooks into Better Reflection, it does the reflection, and of course you can cache it and so on, because you don't want to do that every time because it's slow, and you don't want to slow your websites down. But you can theoretically do monkey patching, although I probably wouldn't do it, right? Just submit a pull request to your favorite library that you want to monkey patch, because that's going to be easier and safer. All right. That is it from me. Are there any questions? Thank you.